Well, welcome back, folks. I hope you're enjoying your learning of electrochem. And so that's what we want to continue today. And last time we were talking about um, delta G, right? We were talking about redox and delta G, and we said, hey, there's this relationship between delta G and E, and that is my Gibbs free energy is equal to negative NFE. And we said my N is the number of moles that are transferred in that redox reaction, that E is my cell potential or my reaction potential, and F is Faraday's constant, 96485 joules per volt mole. And then we could also relate that to um, equilibrium K, right? We could relate that to K, and my Kp would be e to the NFE prime over RT, which is just another way to state what we did before with delta G, right? We said Kp is equal to e to the negative delta G prime over RT. Always watch your units on that. And so now we want to take this one step further, and we want to discuss what happens at non-standard conditions, right? So let's take a look at our notes again. Let's pop, oh, here are the notes. Yikes. Okay, let's go with, what do you say, a 5? Let's go with the Roman numeral 5. I kind of like Roman numeral 5. Roman numeral 5, Roman numeral 5. And so let's talk about E non-standard. How's that? Right? We said that our standard conditions for using our table were 1 atmosphere, 25C, and concentrations of my products equal the concentrations of my reactants equal 1 molar, right? We said that was what our standard conditions were for my cell potential, right? Now, what happens if we change that? Well, let's go back and recall. Let's recall what we did with our delta G, right? We said that my delta G is equal to delta G prime plus RT natural log of Q, right? And this was our non-standard pressure adjustment, right? Right here was our non-standard pressure adjustment. So then let's go ahead and make the substitution for my E. We said that E is equal to negative NFE, excuse me, delta G is equal to negative NFE. So that would mean delta G prime is negative NFE prime plus RT natural log of Q, right? So let's divide everything by minus NF. So we get a minus NF, and a minus NF, right? And so that means what? That would mean my E is equal to my E prime minus RT over NF natural log of Q, right? And that indeed is a correction. This is our correction for non-standard. This is actually for non-standard pressure and non-standard concentrations. Now, you can use this, watch your units, make sure your units cancel. So if we are in joules per volt and F, then you need to make sure you're using 8.314 joules per mole Kelvin there, right? Now, there's a famous guy, I have no idea who he is, but he's called Nernst. And Nernst kind of simplified this a little bit. And I don't care which of these you use. This is on the AP exam. Nernst is used very much in college. And Nernst simplified this to, I don't know if it's simplified, but he put in some values, 0.592, 0.0592 over N, and then he went into the regular log, not the natural log of Q. All right? And so I don't care what you're using, whichever one makes you the most comfortable. But they both work, and really, if you these are both the same equations. All right, Good, so there we have it. So let's take a look at a problem. Here I go. I have this reaction between dichromate and iodide. All right, it's at 1 atmos and 298. However, my concentrations are not 1 molar. So that means I have a non-standard situation. So the first thing I kind of need to do is recall what this reaction is. I don't recall, so I better start from the beginning. So I have dichromate, and I know that dichromate is going to, it's a strong oxidizing agent, so I know it is going to reduce to chromium-3. I have 2 of these, right, because I have 2 chromiums. I need to add 7 waters over here, which means I need 14 H pluses here, which means I need, what, 14, and minus 2 is plus 12, and I think I need 6 electrons, right? Let's make sure I did that right. 14 minus 6 is plus 8, minus 2 is plus 6, 2 times plus 3 is plus 6. Okay, that's good. And then my iodine has to oxidize, right? So that would mean I'd have my I minus 2 of them going to I2 plus 2 electrons. You guys buy that? Yeah, I kind of buy that. And let's see, I have negative 2, negative 2. I have my electrons on the opposite sides. I'm going to have to multiply this by 3, right? And then what happens? I get 14 H pluses plus dichromate plus what? 3 times 2, 6 I minuses. I should actually put in my states here because those will be handy for us soon, right? Yields what? 3 I2 solid plus 2 chromium 3s aqueous plus 7 H2O liquids. There we go. So that would be my balanced equation. And I need to get my E, right? Oh, let's see here. I need to get my E. Let's move this down. There we go. So I'm going to need my E. So my E prime for this reaction is going to be, okay, so what is oxidizing or what is reducing? We know my dichromate is reducing. So I need my standard reduction potential for my dichromate minus the standard reduction potential for my I2, right? Good. So let's go check those out. I have my mighty table back here still. Ooh. Somewhere. There it is. So what's my dichromate? I probably should have memorized this one by now, right? Dichromate, where is it? Here is my dichromate. It's a 1.33. 1.33 volts. Good. What is my iodine? I've used that a lot. It's like 0.5 something, isn't it? Here's my iodide. My iodine going to iodide 0.536. 0.536 volts. Okay, so then let's zip ahead. Oh no, I don't want that. Done. I was going too fast. It's like talking to you guys in the morning. Too fast, I lose you all. Good, here we go. My dichromate is 1.33 volts minus my iodine 0.536 volts and oops, clear. Hey, oh my gosh, everything's crazy here. Okay, here we go. Let's try this. 1.33 minus 0.536, and I get a 0.794 volts, although that 4 is not going to be significant, is it? All right, so here we go. Let's look at our Nernst. Our Nernst said what? E is equal to E prime minus, you guys remember what it was? Minus what? Minus RT over NF natural log of Q. Okay, RT over NF natural log of Q. RT over NF natural log of Q. All right, so that would mean I'm going to take my 0.794 volts minus R, 8.314 joules per mole Kelvin times my T. We said it was 298, right? Let's go up there and check it out. But I'm pretty sure it said 298, right? 298, yep. 298K over N. How many electrons were transferred in this reaction? Well, what? 6. So I have N of 6. And then what? 96485. 96485 was my joules per volt mole. Joules per volt mole. And so everything kind of cancels out, right? My moles are both in the denominator. My K's cancel. My joules cancel. And I'm going to have 1 over volts, which makes it volts. And I have the natural log of Q. But now what's my Q? I have to look at my reaction to decide what my Q is. So my Q would be what? I've got concentration of chromium squared, right? Anything else? No, not on that side. Divided by what? The concentration of H plus to the 14th, concentration of dichromate squared, concentration of I minus to the 6th, right? Everyone see where that's coming from? That's coming from my coefficients in my balanced equation. And then we need to put in the numbers. What do I have? I have 2 for my dichromate, so I'm going to put a 2 there. And I have 1 times 10 to the minus 5th for my chromium. 1 times 10 to the minus 5th for my chromium. You guys all believe me on that? 1.0. And then my other 2 are 1. So this would be 1.0 and 1.0. So let's calculate our Q here. I guess we can drop these in. Well, I better be careful. Let's write it all out so I don't make any mistakes, because you all know I'm challenged sometimes on that. 0.794 volts minus 8.314 times 298 divided by 6 times 96485 times the natural log of 1.0 times 10 to the minus 5th squared over 1.0 to the 14th, which is 1, times 2.0 squared times 1.0 to the 6th. How's that look? Let's go back and make sure I did this right. Right, I have a square to the 6th. Oh, this is not squared. My dichromate is not squared. That would have been a mistake. Ay, caramba. Doink, get rid of that. This is not squared. It's just a 2. There we go. Whoo! That could have been a whole big mistake. Okay, so that is everything good. Up here, we have 1.0, 1.0 for my iodide, and for my hydrogen, my chromium 3 is 1.0 times 10 to the minus 5th, and 2.0. All right, I think that looks good. 1.0 times, yeah, beautiful. So now let's run the numbers. Are you ready? Got to be careful here now, because there's all kinds of ways we can mess up. So I'm going to take this slowly. 1 times 10 to the minus 5th. Okay, 1 times 10 to the minus 5th. And I'm going to square that puppy. Good. I'm going to divide it by 1. Divide that by 1. That's all redundant. This is going to divide it by 2. There we go. And I get 5 times 10 to the minus 11th. I want to take the negative log of that. No, not the negative log, just the natural log. Take the natural log of that. And I get negative 23.7 times 298 divided by 8. Nope, not divided. Let's change that. Times, let's change that. Times 8.314 divided by 6 divided by 96485 equal, take the negative of that, right, because I have to subtract, so I have to take 0.794 minus my answer, and I get a 0.8968955, but we only said what? This was not significant, so we get 0.8. Well, no, we get 0.90 when I round it. It was 0.895, but when I round it, I get 0.9 volts. And so my driving force actually increased because of this change. Now let's make sure I did this all right. Let's try it again. I'm going to try this left to right this time. 0.794, right? Minus a big quantity, 8.314 times 298 divided by 6 divided by 96485 times quantity natural log of 1 times 10 to the minus 5th squared divided by 2, right? Quantity. I get 0.8955. Woohoo! My calculating skills actually work. Beautiful. So that is what we do in case we have a non-standard temperature or pressure. All right, you guys try this one. Bring me back when you're ready. Okay, here we go. You guys got ready real fast there, didn't you? So I even gave you the reaction. And so the first thing I have to do is calculate my E prime, right? So my E prime is going to be, I have to identify what is oxidizing. Well, aluminum's going from a 0 to a +3. So my aluminum is oxidizing, which means my iodine is reducing. So I'm going to get my standard reduction potential for my I2. And remember, I don't care about the coefficients because standard reduction potentials are intensive. Minus my standard reduction potential of my aluminum 3, right? Good, so let's go back. And I'm going to need, I know we calculated this before. That's okay, we can calculate it again. It's good to do that. In fact, I just went by it, didn't I? Okay, where's my iodine? We should know that by now. It's 0.536. And what would be my aluminum? My aluminium is a negative 166. Negative 1.66. Good, I think I can do the calculation now. Ah! Man, come on, got to work with me here. Board, yeah, technology. It's going to take over our lives. We're all going to die from it. Just remember that. Okay, good. What was my iodine? My iodine was 0.536 volts minus my negative 1.66 volts. You know, that's a negative and a negative positive. So it's 0.536 plus 1.66, and that looks to me like that's a 6, that's a 9, that's an 11. How about a 2.196? Wow, I can do that old school way too. Isn't that cool? Good. Of which that 6 is not going to be significant. All right, so now we need to put together the rest of the mess. So, oops, yeah, so let's write down our equation. E equals E prime minus, what was that? RT over NF, natural log of Q, right? So then I have my E prime, which I said is 2.196 volts, minus R, 8.314 joules per mole Kelvin, times my 298 Kelvin, divided by N. How many electrons are transferred? Well, like I said before, we can look at this. My aluminum is going from a 0 to a +3. So how does that happen? It must lose, what, 3 electrons to do that. And that's happening twice, so my N is equal to 6 electrons. So I have 6 again. Wow, that's a coincidence, isn't it? My F is 96485 joules per volt mole. And then what's my Q? My Q is going to be concentration of my aluminum, right? Concentration of my aluminum, what? Well, it's squared. Concentration of my iodide to the 6th over the concentration of 1, right? That's it. Good. So I don't have anything in the denominator here. Let's get rid of that line then. There we go. Cool. Right? I think that is it. All right, let's drop these numbers in. What do I have here? This would be 4.0 times 10 to the minus third, and I'm going to have to do what? I'm going to have to square that. And this is 0.010. Is that correct? Yes, and I have to do what to that? I have to the 6th. Okay, let's run the numbers. Let's see if I can do this right. Grabbing my handy dandy TI-84 because I can't do logs and natural logs in my head. I'm going to take 0.01 and I need to take that to the 6th. Okay, so that could be what? Square it, square it, square it. And then I can multiply that times 4 times 10 to the minus 3 squared. And I get 1.6 times 10 to the minus 21st. Now, does that make sense? This is what? Just before you do this, is 1 times 10 to the minus... Yeah, so that's 1 times 10 to the minus 12th. And then that's to the minus 6 minus 18th. 2 times that is 12. Does that make sense? Nah, something's wrong. Let me redo that. One times 10 to the minus 2. Oh, man, make a mess. Let's try this again. 0.01. Now, let's see. I need to take that to the 6th. Where is that on this calculator? I guess I have to do the caret to the 6th. How's that? There we go. I get 1 times 10 to the minus 12th times 4 times 10 to the minus 3rd, and I'm going to square that. And I get 1.6 times 10 to the minus 17th. Take the natural log of that. I get negative 38 something, right? Times 298 times 8.314 divided by 6 divided by 96485. And I get a negative 0.1655. So I'm going to take 2.196 minus my answer. And I get a 2.36 volts. So once again, my reduction potential went up, meaning my driving force became greater for moving this in the forward direction. All right, how are you guys doing with this? Perfect. Okay, now let's just stop right here, and when we come back, we're going to use this for another purpose. All right, cool. I hope everybody's having fun.